So in the previous session we have learned about the electric field. In this session we shall discuss about the electric field lines. Electric field was a vector quantity. Okay, here we shall try to understand it by some pictures. Electric field lines are the imaginary lines which starts from a positive charge and goes up to infinity or terminates to a negative charge, and it never forms closed loops. Okay, so for unit positive charge, for an isolated unit positive charge, if you take an isolated unit positive charge, then this is suppose plus q charge, then electric field will start from this point and goes up to infinity. Okay, this denotes the it goes up to infinity, dotted line. So starting from the unit positive charge, it goes radially outward up to infinity. Okay, it goes up to infinity. One may draw infinite number of field lines from a particular point charge. Okay, we have drawn several. Now at each point on the field line, we can get the direction of the field. The field line itself denotes the direction of electric field line. In case of a curved line, if we draw a tangent at any point, then we will get the direction of electric field at that point. And the relative closeness or the density of the field lines denotes the strength of the electric field at that point. So when we move far away from the charge, the density is less, so the field is weak. And when we move towards the charge, the density of field lines, the electric field lines are more dense, so the strength of the electric field is high. Okay, that is the magnitude of the electric field, or the intensity of electric field is high near the charge. Okay, for isolated negative charge, the lines are directed towards the charge. Okay, for isolated negative charge, the lines are directed towards the charge. We cannot break the line at any point. Okay, this is a continuous line. This dotted lines represents that it goes up to infinity. For isolated charge, it goes up to infinity. The lines can't be broken. Okay, dotted line represents that it goes up to infinity. So this is for a isolated positive charge, this is for a isolated negative charge. For a isolated positive charge, it starts from the positive charge and goes up to infinity. And for a isolated negative charge, it starts from infinity and terminates on the negative charge. Okay, and in both cases, the field lines denotes the direction of the electric field. That in case of positive charge, it is directed away from the charge in the radially outward direction, and it is directed towards the charge in radially inward direction. Okay. Suppose we have a positive charge and a negative charge separated by a distance. Then electric field lines will start from the positive charge and terminate on the negative charge. Some of the electric field lines will start from the positive charge and terminate on the negative charge. So these are the field lines for a positive charge and negative charge separated by a distance. So if you want to know the electric field at any point, the electric field denotes the direction and magnitude of the electric field. The direction at any point is given by, suppose we want to know the direction of electric field at this point. So if we draw a tangent, this tangent will represent the direction. If we draw a tangent, this tangent will represent the direction of electric field at this point. If we draw the tangent here, it will be in this direction. Okay, so the tangent will give the direction of electric field at each point on the field lines. Okay, and the relative closeness, the density of the field lines will represent the strength of electric field at any point. Okay, now suppose two positive charges are separated by a distance. Okay, in this case, the field lines will start from the positive charge and goes up to infinity. So these are the field lines for okay. So these are the directions of electric field. These are the representation of electric field lines for a positive charge and negative charge separated by a distance, and two positive charges, that is two like charges separated by a distance. If you remember the previous problem, when we have for the first problem, two charges plus q and plus q separated by a distance, we are interested to find out the electric field on its perpendicular bisector. Then it was along the perpendicular bisector at somehow this point. Okay, so it was somehow at this point and the electric field was directed along the perpendicular bisector. And the second problem, the electric field is directed in this direction, again on the perpendicular bisector. Okay, so this is also evident from these field lines that the direction is along the tangent. Okay, so this is for the positive and negative charges separated by a distance, and this is for two like charges separated by a distance. Remind that two field lines never intersects each other. Okay, because the direction of field lines at a point is unique. There is a both the magnitude and direction at a particular point, that is the electric field at a particular point is unique. That is, it has only one direction and its magnitude is also fixed. Okay, so if two field lines intersect at any point, then we can draw two tangents at the intersection point, and it will represent two directions of the electric field in the same point. So it is not possible to intersect to get the intersection of two field lines. Okay. Now, what is electric flux? Next is electric flux. Okay. Electric flux gives the measure of electric field lines passing through any area. It gives the measurement of electric field lines passing through any area. Okay, so how one can measure the amount of flux passing through any area? So the area should be held perpendicularly with the electric field. Suppose E is the electric field at any region, and we are interested to find out the flux through a uniform surface S. So area is a vector quantity, and the flux due to E through S is given by, flux is represented by phi equal to E dot S. Okay, for any arbitrary vector, suppose a vector is A, not about the electric field. For any arbitrary vector, it may be electric field, it may be magnetic field, it may be gravitational field. Okay, so for any arbitrary vector, the flux through any elementary area ds is given by phi equal to A dot ds. Okay, so small amount of flux passing through any elementary area is given by A dot ds. So what is flux? Flux is the measure of field lines passing through that given area. So here d phi represents the amount of field lines, passing through ds, amount of field lines due to vector A passing through the given area ds. Okay, suppose this is an area, so it gives the measure of field lines passing through any area. Okay, suppose E equal to 4I plus 2J minus 4K Newton per coulomb, and the area vector is given by meter square. This is the area vector. Okay, then what is the electric flux passing through the given surface S due to the electric vector E? So the flux, what is flux? Flux is the measure of electric field lines passing through any area. So the flux is given by E dot S, and it is 4I plus 2J minus 4K dot 40 I cap minus 20 J cap. Okay, so this is if you perform the dot product, then 4 into 40 plus 2 into so unit is Newton meter square per coulomb. Okay, so we shall discuss the next part.